Yeah, so thanks a lot for the introduction invitation. Yeah, it's really a pleasure to be, in the internet with all of you. Yeah, I should preface this by saying I'm a little rusty on Zoom. It's like the kind of things you sort of get really good at during like, 2 years of like, isolation. They just leave you immediately. So yeah, please stop me if you can't read my writing or if you have any questions. Yeah.
Wait, Matt, can you have your screen, your iPad has a little video. Can you slide it to the side?
Oh, how do thank you. Thank you. Yeah.
Thank you.
Wonderful. Yeah. Okay, yeah, so yeah, but it's great to be back. And you know, um yeah, uh yeah, in the internet. And it's, unfortunately I had to teach, so I still have pants on, but anyway. So right. So I want to tell you about some relative Thom type conjectures for surfaces and four manifolds with boundaries. So let me just remind everybody about the ordinary Thom conjecture. So this is such a beautiful conjecture and subsequent theorem. I think at least for me when I was starting out in math, this was really kind of an inspiring selling point for our area. So if you have so if sigma is a smooth surface, which is say complex curve, and X omega J Kähler manifold, then it minimizes genus in its homology class, which we could phrase as negative. Its Euler characteristic is less than or equal to that of any other surface, which is smoothly embedded and shares its homology class in H2. So this being, very striking, given that this is such a rigid condition you would place on surfaces, and notably that it fails in the topological category, the sort of locally flat surfaces. And you can relax this and just look for a symplectic surface and a symplectic four manifold. And this would be called the symplectic Thom conjecture. And so, this has a long history. I think maybe Thom raised this question pertaining to CP2, but it's been subsequently proved in complete generality. So his first Kronheimer-Mrufka proved some special cases of it for some certain class of Kähler surfaces in the context of instanton Floer homology. Notably missing in that treatment was the original case of CP2, which they then proved in the advent of Seiberg-Witten theory. So this was also proved in concurrently using similar techniques by Morgan, Sabo, Taubes. So this is ASD. This is Seiberg-Witten. And then Osvat and Sabo proved the general case of symplectic Thom conjecture. And so indeed the symplectic Thom conjecture in many cases was proved for surfaces of positive or non-negative square. So let me remind you how this goes, because we're going to sort of try to think about a development along similar lines of a relative version of all this. So the first ingredient is this classical adjunction formula, which is more or less just the Whitney sum formula for characteristic classes, in this case, the Chern classes, which gives us a genus formula for complex curves. So this says, if in the situation above, we have negative C1 of J, the complex structure in question, evaluated on the homology class of this curve, plus the square of that homology class equals negative the Euler characteristic. And so, this being equal to 2G minus 2, this gives us a nice method for computing the genus of a complex curve if you know the Chern class of the complex structure in which it sits. And so the proof of this is just the Whitney sum formula. The fact that this is a complex curve, or more generally a symplectically embedded surface, gives us a splitting of the tangent bundle to X along sigma. This is the splits as the tangent bundle, the complex tangent bundle of the surface, plus the normal bundle. And so taking Chern classes, first Chern class here, because we're dealing with the surface, a bundle over a surface. We get this, and then evaluating on class of sigma. More or less immediately yields the formula. So this is this left-hand side, or right-hand side rather, is equal to the Euler characteristic of sigma, the first term, and then the second term is the self-intersection, or the number of zeros of a generic section of the normal bundle. So rearranging the terms, we get it. Okay, so that's the first ingredient. So if you had a complex curve, you know what its genus is, and now you want to say that that's the best possible, and then this goes comes from the adjunction inequality, and this is where gauge theory enters the picture. So if you have a non-vanishing result for some four-manifold invariant of the types that we understand and have seen, to this stage in history, then you get this adjunction inequality. So let's, in this case, assume that W is symplectic. So Taubes in this situation gives us a non-vanishing result for the Seiberg-Witten invariant of W. So, and he says that in the spin C structure, corresponding to the almost complex structure, we have a non-trivial Seiberg-Witten invariant, which then gives us this adjunction inequality. For any smoothly embedded surface in W. Okay, and then combining these two together, so let's, and the adjunction inequality, this could be any smoothly embedded surface, so maybe I'll put a prime there. But on the other hand, the adjunction formula gives us this. And so we have now that all the other surfaces have larger or negative Euler characteristic. So what I'd like to do now today is I want to tell you about a relative version of this and see in what sense we can extend this type of argument, and maybe motivated by what you might call the relative symplectic Thom conjecture, at least initially. So this would say something of the form: let W omega J be a symplectic four manifold with say convex boundary. Some three manifold. And so convex here means that there's a contact structure on the boundary that for which the omega evaluates positively on it. And you can think of this contact structure, and it's going to be very useful for us to think about this as the unique field of complex lines on the boundary. So this is, you take the tangent bundle on the boundary, that's some three-dimensional subbundle of the tangent bundle of W. You hit it with the complex structure, the almost complex structure, and you get some plane field. Okay, and so suppose I have a symplectic four manifold convex boundary, and that sigma is a smoothly embedded, smooth and properly embedded surface, which is symplectic. And whose boundary is transverse to this plane field that you get, this contact structure that you have on the boundary. Then the same statement should hold. Then sigma, minimizes genus and its relative homology class. Okay, so one approach to this, and I think this was known for a while, and it was spelled out in a paper by Gadgil and Kulkarni, is that if you can take that surface that you have, and if you can cap it with cap it in some larger symplectic, closed symplectic four manifold. So get some closed symplectic surface inside of a closed symplectic four manifold, sort of a cap for X. Well, then, what's happening? No, nothing's happening. Don't worry. Nothing's happening for you. Yeah, anyway, okay. Microsoft happened. So anyway. Okay, so you can what they showed, and you can think about trying to attach some handles, say, to your original four manifold in some symplectically compatible way, where then you can close off sigma with the chords of those handles in a symplectic way, and then you can just apply the ordinary symplectic Thom conjecture of Osbat and Szabo, or their resolution of it. And so that works. And so this relative symplectic Thom conjecture in this capacity is known. More recently, Alfieri and Cavallo have a different proof, which is very much in line with what I'm going to talk about now. And in some sense, they did something quite similar as what Catherine and I have had in progress for quite a while. And so there's I guess uses it's closer to what maybe I would say is the proof by the book, in the sense of Erdős or whoever. There's works for Stein fillings, and it draws on some very beautiful work of Kyle Hedden that gives you a topological interpretation of knots and contact three manifolds that are filled by a Stein manifold in terms of notions of positivity in the braid group. But I want to just maybe work even maybe work more naively and just say, well, let's just try to mimic the exact same argument that we use, this two-step, you want an adjunction formula and an adjunction inequality, and think about a proof of that form. And so what I'd like to advocate for is just, following the same proof strategy and first having a relative adjunction formula and a corresponding way to compute the genus of a symplectic or almost complex curve in a almost complex four manifold. So how would this work? Well, the picture I have in mind is I have this four manifold with boundary X. Sitting inside here, I have some surface, and its boundary is transverse to the plane field on the boundary. So I have at every point in the boundary, I have this unique complex line, and the tangent to sigma is transverse to that plane field. Now, the boundary of sigma is lying inside of a three manifold. And so in particular, so I'd like to somehow get a notion of a Whitney sum formula for a relative characteristic class, or for the relative Chern class. And so what I could do is, given a Seifert surface inside Y, the Seifert surface is always going to be S, and sigma is going to be the surface in the four manifold. So this is a surface that sits entirely on Y. So I'll just draw it over here, and I'll indicate that it's in Y because maybe it has larger genus than what sigma had. Well, then inside Y, I have I have the intersection of those planes, the contact planes, with the tangent planes to the Seifert surface. And so this is some one-dimensional subbundle, and it gives me a section of that bundle over the circle. Gives me a trivialization of, it gives me a section of that bundle. So I'll call this the section of the normal bundle along. So this is a section of the normal bundle to sigma along its boundary. And then I also have a section of the tangent bundle to sigma. So I have what I'll call S tau. This is just the tangents to sigma. So this is a section of the tangent bundle to sigma along the boundary. And so, what the relative adjunction formula, what you might mean by that then, is like a Whitney sum formula for the Chern class. So you could define a Chern class of X. So X is a perfectly good almost complex four manifold. So it has its complex structure on the tangent bundle. It has a Chern class. You can restrict that to the surface in question. And I have a trivialization of that bundle along the boundary, which splits as a direct sum of two sections of the two independent lines. I have the section of the coming from the tangent to sigma, and I have the section coming from my Seifert surface. That's a section of the normal bundle. And so then we correspondingly have a Whitney sum formula for the relative Chern classes of this form. So remember, tau is the tangent to sigma. So that's a section of its tangent bundle. It's a non-zero section. So it trivializes the bundle there. And then I have a section of the normal bundle. And I have the normal bundle to sigma, and I have a section along its boundary, which I'm denoting S nu. Okay, and so you might wonder, well, how would you prove such a formula? Well, I mean, the first thing you do, because we're a low-dimensional topologist, so we tend to think of Chern classes in terms of obstruction theory. And so you could think about proving this in terms of obstruction theory. So here's the formula. So the first thing you would think to do is to just try to work with obstruction theory. But if you do this, you have to try to make sense. You say, well, I can define these obstructions and they can add this way, but you would like them to be, have all the properties that you have of characteristic classes that we know and love. So for instance, we'd like the Whitney sum formula to imply something like this. So you could do that, and initially that's the way it started to proceed. But the other thing you could do is you could just develop a whole theory of relative characteristic classes. So what would I mean? What would this look like? This would say, suppose I have a vector bundle, or a fiber bundle more generally over some base. So here's some fiber bundle, and suppose I have sitting inside of that base, I have some subspace, maybe, which I denote K, because in this case, K, is the boundary of our surface, which I'm thinking of as a knot in a 3-manifold. And so I can, sitting inside of my total space, then I have the bundle restricted to K. And if you have, say, a trivialization of that bundle along the subspace, well, then you might hope to be able to define a relative characteristic class or collection of relative characteristic classes. Maybe you'd want to denote them. They depend on this trivialization. Sometimes you might want to denote them in underline. And these would be cohomology classes associated to this bundle and that trivialization, and they should live in the relative cohomology of B relative to the subspace. So you could, and indeed, this has been developed. So thankfully. Crever, totally did this. He did everything that we want out of the theory. He developed. He was, oddly enough, I think, motivated by a kind of similar problem stemming from identifying certain numerical invariants arising in stable homotopy theory from the Pontryagin and Thom construction. So it's sort of not unrelated to what ultimately we end up considering. But the title of the paper is just Relative Characteristic Classes. It's an American Journal of Math, sometime in the 60s, I believe. And so given that, so you get this formula just as the sort of relative Whitney sum formula. When you look at this, how do we then get this genus formula that was so useful in studying complex curves and closed complex curves and complex surfaces? The genus formula is a little bit more subtle. So, we want to somehow, here we have the, up here, the relative Chern class of the tangent bundle relative to a section, relative to the tangents to the surface. So that will give us the Euler characteristic indeed, if we evaluate it on the relative cohomology class of the surface. But the other terms are a little bit harder to understand. And so, so let's now, given everything as above, I claim that there's the following formulas that if I evaluate the absolute Chern class of X on, so here, if I put sigma, that's a relative homology class. But what I can do is I can take the Seifert surface that I used in the definition of my trivialization to define the section of my normal bundle along the boundary of sigma. I can use that to get a closed surface. So here's sigma S is sigma union minus S along the common boundary. So that's now an absolute homology class. I can take its square, or its intersection under the intersection form. And in the genus formula that we know and love, this right hand side now is the Euler characteristic of sigma, or the negative Euler characteristic of sigma. But we get a correction here, which is the self-linking. So remember that the boundary of sigma was transverse to that plane field that we had on the boundary coming from our almost complex structure. And so if you have a curve in a three manifold that's transverse to a plane field, then I can define this this self-linking. So in general, that self-linking will, if you're familiar with contact geometry, if you have a knot that's transverse to a contact structure, we often see that the self-linking number we think of as a number that depends on a relative homology class of Seifert surface. And it, of course, depends on the plane field. And so I claim that there's a formula of this form where you get a correction for the self-linking. So let me just tell you a little bit about how you might prove that. So it's here where I try to do something that just totally failed. I tried to save myself some time here, and I practiced it once and it worked, so I thought that it would work again. And it's not. So okay, great. Well, oh no, yeah. Okay, all right. I have to abandon this. Okay, so or else it was so beautiful. I had this. If you look up here very closely, you can see these little tiny numbers, and those numbers are the equation lines for some equations that I so carefully wrote out because I knew it would take me like 10 minutes to write the equations, and then I carefully like colored over them with white. And then, I put the one there so that I would know what to erase when I cut and pasted this. And it was going to you guys were all going to be so impressed and think that I was really responsible, but whatever. Okay. So what are we supposed to do here? So there's this key naturality property for relative characteristic classes that if you have a relative class for a bundle, you have this inclusion-induced map to absolute cohomology on cohomology. And so if you have some relative class of a bundle, this is going to map to just the ordinary characteristic class for that bundle. So forget about the trivialization you had over K. And so so C1 of J now, this is an absolute characteristic class. For a bundle. And so I can think about that as the image of this relative class evaluated on this relative homology class. Okay, and so now I can take the adjoints. I have C1 of J or C1 of X evaluated on push forward of sigma S. And now, so this is the push forward. So that's an absolute homology class now mapping into relative homology classes. And this will map to the difference. Oops. The difference of these classes. So I have so this right being a little bit So this is I can think about the relative characteristic class for the tangent bundle restricted to sigma. Okay, so then if I expand this out, I have C1 of Tx restricted to sigma relative to this trivialization that we discussed above. Okay, so we have these, we get these two different terms, which are evaluations of relative Chern classes on relative homology classes. And each of these breaks up according to the Whitney sum formula that we have. So in both cases, we have a splitting, and one reduces to, well, this is C1 of T sigma relative to the trivialization that we get by just the tangent vectors to sigma along the boundary. Plus plus the term coming from the normal bundle. And here I'm using the fact that I've assumed, either by the fact that sigma is a symplectic submanifold of a symplectic four manifold, or if you like, a almost complex curve in an almost complex four manifold, that I have this splitting of the tangent bundle of the complex tangent bundle to X along sigma. Maybe I'll color the second one in two. So the second part also breaks into two terms. So notice that here, this is now the tangent bundle to X along S. But S is living inside the three manifold, so I might as well think of this as this is the tangent bundle of Y cross R. So so S is living inside of Y, which I can think of as itself sitting inside of Y cross R, viewed as maybe the symplectization of the contact structure in the boundary. And I can then evaluate, and so I have a distinguished pair of sections along the boundary there as well. And so this will also turn into a sum of two terms. So how do I think about the tangent bundle times R? Well, I can think about this bundle as being the bundle of two planes that I have coming from the complex structure, plus another complex line bundle, which is just, if you like, you can think about it as R dt. So R being like a Rabe vector field, or a distinguished co-orientation, of the orthogonal complement to the plane bundle, and dt coming from the R direction in the symplectization. And so then if you think about that, this Whitney sum formula gives you this evaluation. Of relative Chern classes. And And so now we can think about what all these terms are. So this term, this is just the Chern class of the tangent bundle of sigma evaluated on sigma. So this gives us the Euler characteristic term. Okay. This term, well, this is the Euler class, the relative Euler class of the normal bundle to sigma relative to a framing on the boundary given by the Seifert surface nu. So that nu was like, that was a direction or a framing that's coming from the Seifert surface that I chose. And so this you can evaluate and realize that this is, because I've chosen that Seifert framing, this is none other than the self-intersection of the capped off surface. On the other hand, so now in this second term, well, this is now the relative Chern class of a plane field on the boundary relative to the Seifert framing. So this is what you would think is going to be negative the self-linking of that transverse knot that we have on the boundary. But that negative turns into a positive because of the fact that I'm capping off this knot with the Seifert surface living inside of y cross 0. So S is living inside of y cross 0 inside of y cross an interval. So really, I've reversed the orientation of y where I'm performing this evaluation. So this ends up being just the ordinary self-linking. And then finally, this final term just vanishes because that bundle is already trivial. I have a global section of that bundle given, say, by the R direction, if you like, and I can use that basically to argue that I don't have anything here. Okay, and so if we group these terms, those are the three terms that you have here, here, and here, and I've rearranged as it before. Starting with I started the whole procedure with this evaluation. Okay, so great. So we have this genus formula. And so now how do we prove a relative Thom conjecture given a genus formula? Well, again, just as above, we want to combine the genus formula with a relative adjunction inequality in this case. So relative adjunction inequality, just as adjunction inequality plus genus formula gave us the Thom conjecture, relative adjunction inequality plus relative genus formula should imply relative Thom conjecture. Okay, so let's just see that play out. Maybe I'll cut and paste here. So there's sort of two ingredients for how to make this work. So the relative adjunction inequality, what this is going to say in the present context is, given x 4 with boundary x equals y, and J, an almost complex structure. So for these purposes, really, it suffices to have a spin C structure on X, which is an almost complex structure on the complement of some balls. Up to a notion of equivalence. And so here, then I get an invariant of that 4 manifold. The almost complex structure on X has a spin C structure. I'm denoting S of J, and this invariant lives inside of the Floer homology, let's say the hat Floer homology of the boundary. And so supposing that this is non-zero, then with Catherine, we have proved an adjunction inequality of the form the Chern class of that spin C structure associated with the almost complex structure, or the almost complex structure, the Chern class of it, evaluated on one of these capped off surfaces plus its self intersection. So the adjunction inequality would tell us you have something of the form negative the Euler characteristic, which would be like 2g of sigma minus 1 in this case, because this is a surface, say, here I'm assuming there's a single boundary, everything's going to extend to lengths if you like, so I'm not going to focus on that. But so we proved that we have an adjunction inequality of this form, but there's like a correction coming from a numerical invariant. So this invariant here, maybe I should call this alpha. This is the relative invariant of that four manifold in spin C structure. And so to any Floer homology class in any three manifold, like accepting the zero class, I can define a number. So this is a knot in a three manifold, or a link if you like. This is a Heggard-Floer hat class. And from that, you get a number. And this uses the fact that knots in three manifolds filter the Heggard-Floer chain complexes associated with those three manifolds. And then you can, if you have a filtered chain complex, any homology class for the homology of that complex gets assigned a number, which is like the minimum filtration level where that class starts to be seen in the filtration of the homology associated with that spectral sequence. So this sometimes in this maybe the more symplectic world, like this is these are these are sometimes referred to as like the spectral invariants. So we get this number, and or maybe and if if you like rationally no homologous knots or links, then maybe this number is going to be in Q. So all of this will extend to that context as well. But so we show that these numbers are sort of a stand-in. They give you a refinement of the adjunction inequality that you'd expect for closed surfaces. So that's half of it. So if we look back up here, notice that if X is symplectic, then Sj and Sj, the sort of complex conjugate spin C structure, both have non-trivial invariants. And so then we can get this formula, or this adjunction inequality. For the relative invariant of the symplectic four manifold, and I can put a minus sign there, but at the expense of maybe conjugating. Okay, so there's that. Oh, sorry, and there's no minus one here. This is 2G. Okay.
Not.
Yes.
Sorry. So you're saying that in Heggard-Floer homology, we know that the relative invariants of any symplectic filling are non-zero?
Weak symplectic filling. If I'm willing to use twisted coefficients, which I'm happy to use if if somebody wants that, like this will all work in that capacity.
Okay. This follows just from the okay, yeah, I see. You close it up.
So I mean, if you want to not work with twisted coefficients, then maybe I want to think about strong symplectic fillings of a contact green manifold.
Yeah.
There's also there's these issues that I know you're familiar with about kind of naturality issues with regard to different types of symplectic cobordisms, and then you wouldn't necessarily just have like one Floer homology class and the Floer homology the boundary, but you'd have like a map between Floer homologies, and you want to know sort of whether the contact class for the incoming manifold is mapped to the contact class for the outgoing manifold, and there's sort of issues there that are, I think, still unresolved, but and how natural those maps are. But here I'm just assuming that I have a filling of the three manifold. Right. So okay. So this is the relative adjunction inequality, but I had introduced these like generalized tau alpha invariants some years before Catherine and I sorted out all of the relative adjunction inequalities, and the purpose there was this interesting bound that the self-linking, say if alpha is equal to the contact class associated to a contact structure, and this is non-zero, then I had proved an inequality which was really inspired by Olga Plemenevskaya's corresponding result for the tight contact structure in the three sphere, which said that the self-linking, maybe I'll suppress the Seifert surface here. Maybe I won't. The self-linking of a knot is bounded above bounded below by twice bounded above. Sorry, yeah, okay. Bounded above by twice tau okay, -1. Okay, so this is like a relative Thurston-Binnikin type bound for self-linkings of transverse knots in contact manifolds. Okay, so if I combine this and this, then I get so I take this inequality and I have plus, I add self-linking. Okay. So this is going to be bounded by 2 tau of the contact class on the boundary of this symplectic manifold -1. And then the relative adjunction inequality, subtracting 1 from both sides, gives me that this is less than or equal to twice genus of sigma -1. Okay. Now, on the other hand, the adjunction formula or the genus formula that we proved, just using characteristic classes, says that this is equal to the twice the genus of sigma -1. And so we've shown that, I guess this inequality holds for all surfaces, whereas, if I have a symplectically embedded surface or a J-complex curve and an almost complex Floer manifold, then I have equality. And so So the string of inequalities is sharp. Hence, we get this relative symplectic Thom conjecture. Okay, so, I want to so in some sense, I had wanted to prove it this way years ago, and Catherine and I had, figured this proof out at some point. But what's held us up for a while is, thinking about, in what sense this might generalize beyond the symplectic setting. And so let me just conclude with some remarks about that. So again, in what sense is this about symplectic or complex? So where are we using that here? So let's suppose that let x omega j be let's just let it be an almost complex Floer manifold. With omega, omega is not going to be a symplectic form, but omega maybe is non-degenerate. So if I have an almost complex structure, I can always find a non-degenerate two form that's compatible with it. That's some other. This is the kind of 2 or 3 lemma symplectic and sort of affine symplectic geometry pushed into manifolds. So suppose I have a almost complex Floer manifold with a non-degenerate 2 form, and sigma is a smoothly embedded surface such that what? Well, the first thing is I still want the boundary of sigma to be transverse to the plane field on the boundary. So this is ty intersect jty. And I just want to emphasize here, I don't want to, let's not assume that this is a contact structure. This is just some homotopic, this is some plane field. And what else would I want to, what else might I want to assume? I might want to, and suppose that sigma is, either J complex. So that would mean that, J of T sigma equals T sigma. Or, we could, another thing that you could do is just assume that this is a symplectic form on sigma. So it's a non-degenerate 2 form on X, might not be closed, but it's certainly closed on sigma in a BS. So then we'd have a symplectic submanifold. So the question here is, when is sigma minimal genus? In its relative homology class. And so we're going to have to put some assumptions. It's categorically false in general. For instance, any knot or link bounds a symplectic surface of any genus and any over twisted, and sorry, I should say in the symplectization of any over twisted contact manifold. So this is some kind of topological argument. But kind of curiously, to me at least, that that there are ways, even in this over twisted setting, there's certain situations where we can prove that symplectic, properly embedded symplectic surfaces still minimize genus in their homology class. And so what we need out of this, let me add some assumptions here. So I need to have some assumption on this plane field. I don't need it to be a contact structure. And I also, of course, I need some assumption on my four manifold. I need some gauge theoretic assumption, because I'm going to use the relative adjunction inequality that applies to spin C structures on four manifolds with boundary that have non-trivial map on Floer homology. So I need Fx. So I need the spin C structure associated to that almost complex structure. I would need its relative invariant to be some non-zero Floer class. There's no getting around this. Call that class alpha. And what do I need out of the plane field on the boundary? I don't need it to be a contact structure, but I do need that there exists a contact structure homotopic to J. Of course, there's a homotopy, there's contact structures in any homotopy class, but I need to find one such contact structure whose contact class equals alpha. So I do have to have a tight contact structure on my three manifold. This is the, C will necessarily be tight because it has non-zero contact invariant, but I don't need it to be fillable. I don't need X to be a filling of this contact manifold. And so that's that. So there's one final, so this is almost enough to get the theorem or to generalize, but I also need one curious assumption as well, that I'm going to add three. So the boundary of sigma is a transverse knot, transverse to some plane field, and I need that the self-linking number of the boundary of sigma, so that's some, if you like, integer associated to the boundary of associated to the boundary of my surface in the four manifold. I need this to equal the self-linking of boundary of sigma with respect to C. So this is some transverse rep of boundary of sigma in C. So, what this assumption does for me, one thing it does is it rules out these kind of easy counterexamples, because those counterexamples are going to have really huge genus. They're going to violate the Thurston-Binnikin inequality for the contact structure that we're assuming here exists. And so this rules out any counterexamples or a violation of the Thurston-Binnikin inequality. But kind of surprisingly, it does a lot more. Like this last condition is exactly the condition you need to construct a homotopy of plane fields from the weird, kind of completely unknown plane field coming from J on my boundary to the contact plane, which is everywhere transverse to the boundary of sigma. So, a very interesting part of this, I mean, to me, like the Floer homology has always been in place. That's been, that's not so interesting to me at this point, because, but to me, what's interesting about the proof here is then that, is that this last condition is really, if you're familiar with Gomph's work on homotopy classification of two plane fields on three manifolds, or the Pontryagin and Thom construction that thinks about these types of objects as frame cobordism classes of frame length in three manifolds. This is a relative version of the Pontryagin and Thom construction, and it's saying that basically the homotopy class of a plane field, together with the self-linking information about for a transverse link, characterizes the homotopy class of a plane field through plane fields transverse to a given one manifold. And so there's kind of a nice argument that goes through here. And to me, at least, I learned something from this procedure. I learned that the self-linking number, although it we define it often in contact geometry, with a Seifert surface, you can actually define the self-linking of a transverse curve to a plane field in a Seifert surface independent way. So even if a knot is not null homologous in any sense, you can think about the self-linking. You can get a well-defined cohomology class associated to a curve transverse to a plane field. And that's something that, I guess I wasn't aware of, through my sort of study of contact geometry. So anyway, I'll stop there. Thanks.
So can I ask a question? So maybe I'm just missing something. I don't really understand the counterexample that you said. I mean, I'm not quite, you're saying that you could make it bound large genus symplectic surfaces?
Yeah, I
So
mean, like if
therefore
the symplectic Thom conjecture were true, then the genus formula would tell you that, like, the genus of a symplectic surface is an invariant of the knot, like it's a well-defined number.
So it's
right?
that it could bound, it's not so much that it could bound smaller, so it's any sufficiently large genus, I guess is what you're really saying.
Yeah, oh yeah, sorry. In fact, yeah, so can we burn the recording, Dave?
Oh no!
I don't know.
No.
It's on 9. I don't know what.
You're done. You're cooked, Matt. You're cooked. We got you.
Thank you, Danny. So sufficiently, yeah. I mean, I'm not gonna somehow produce. I'm not gonna show that every knot slice or something.
Well, it's just somehow I thought I was. I thought you sort of mean like in half of the symplectization or something like that.
Right. So the picture is that I have y sitting, y crossed 1. So this is where.
Yeah, I see. So then,
And I have the symplectization.
You can make a large symplectic surface, so then it clearly can't be minimal. Yeah.
Yeah.
All right.
Sorry.
Okay.
Yeah.
That's what I thought you were saying, but
Yeah. Sorry. I said it quickly because I was running out of time. Yeah.
Yeah. All right. Thank you.
If you're willing to send me your notes, Matt, I will post them with the video. Thought that was the right time to say this. If you wish to edit them and put it.
Yeah. Maybe
you can edit out. We can edit out certain portions for
I don't know, whatever. I mean,
for a fee.
does anybody watch these things?
Are there other questions?
Maybe I have one.
Yeah.
Can you say anything in the direction of like calibrations? Like I think that there's a theorem that says, if you have a surface that's calibrated with respect to something, then it's genus minimizing. And is there any hope that the techniques or the ideas you're using sort of go in this direction or can go in this direction?
I mean, I don't know. I mean, maybe that's what we're doing. I'm not sure. I mean, like, the calibration has to, be I have to find a, I guess a calibrating 2 form is, I think, going to have it's going to have an almost complex structure associated to it. And so then, I can ask whether or not that almost complex structure, its associated spin C structure, has non-trivial relative invariant. If it does, then we prove something. Under this, I mean, at the moment we can't remove this requirement that we have some contact structure in the boundary. So, like, if you have some 3 manifold and you want to apply this technique to analyze the minimal genus problem and certain class of like 4 manifolds bounded by your 3 manifold that to have non-trivial relative 4 manifold invariant, but by other reasons that 3 manifold possesses no tight contact structures. I mean, of course, we don't know many examples like that. Then I don't know. Then this breaks down. I mean, somehow, you know, we're using here. We're using this old result that, like, implicitly, you know, we're using this result that the self-linking numbers of a transverse knot are bounded by like some tau invariant. You know, and like even if it's not a contact structure, if this is just some homotopy class of two-plane fields, well, this inequality still holds for the contact structure you have. So we still get this self-linking bound. I mean, you know, like one case, maybe a special case of your question is like, suppose I have a taut foliation on a 3-manifold. Well, you know, we know there's a non-trivial Floer homology class associated to it. And, you know, of course, it's, you know, very closely related to the, you know, or it agrees, I guess, with the contact class of the Eliashberg, Thurston perturbation of that taut foliation to a contact structure. But this argument is sort of giving you a proof that self-linking numbers of transversals to a taut foliation then, you know, satisfy an analog of the Binniken bound. You know, of course, even in Thurston's original paper, he shows that, you know, the taut foliations satisfy a junction inequality for closed surfaces. But this is like giving you the relative analog of that for surfaces that are for curves that are transverse to a taut foliation. So that's like an area where, you know, maybe there's some partial, you know, progress on what you're suggesting, but I mean, there's some chance that we don't need the contact assumption, but it's going to require like a notion of like Weinstein surgery outside of the symplectic contact world. So, you know, I've thought a little bit about this, about like, you know, can we define sort of almost complex handle attachments and prove naturality with results for certain Floer homology classes under those, you know, almost complex handle attachments that would then, you know, mimic the types of things that we understand for the contact invariant. If we had a good theory there and could really get an understanding of those types of problems, and maybe we know a lot about non-Floer homology and how it behaves, you know, maybe we could, you know, get some nice wide class of manifolds where, you know, that isn't handled by this already.
Okay. Are there further questions? If people are silent, I think we'll imagine that means Matt saved himself and answered all the questions by now, and thank you. So
Thanks, Matt.
Yeah, thank you
Thanks.
guys. Yeah, nice to see everybody.
Well.